morning, everybody. You had a social evening yesterday, and I hope you are awake, reasonably awake and conscious. This is a longer version of the talk I gave on Tuesday in the Aula, and I'm sorry for everybody who hears something now the second time, but I promise you there will be some new aspects in the talk. So, who here in the room has a background in computer science AI? Okay, so I'm sorry for boring you with the first slides. I just want to introduce the area of research which we are talking about. AI has given its name a long time ago, 1956, by John McCarthy, computer science pioneer, inventor of Lisp. First MIT, then Stanford, and AI has from the beginning been a part of computer science research. So it inherits all the core methods from computer science, where we have a strong focus on the design and evaluation of algorithms. The original motivation was when AI was introduced that researchers in computer science who started to do AI research had the assumption that all or maybe many or relevant aspects of human intelligence can be formalized by algorithms and simulated by computer programs. AI has been defined, for instance, in the textbook of Elaine Rich, as the study of how to make computers perform intelligent tasks that in the past could only be performed by humans. The nice thing about this definition is that it doesn't talk about intelligence, which is a rather complex construct, but only about intelligent tasks. When you look at the standard textbook of today, Russell and Norvig, you see that research in AI is around algorithms, formal approaches, and applications addressing many domains where we have an overlap with, for instance, cognitive psychology research, like reasoning, knowledge representation, problem solving, planning, learning, vision, game playing, natural language understanding, and AI robotics. So over the history of AI, we can observe that we had several different kind of core topics most researchers were working on. At the beginning, it was a rather broad collection of algorithms for all the topics I named on the slide before. But then we had in the next phase in the 1980s, some of you might remember, a focus on knowledge representation and reasoning. Prolog has been invented, Lisp machines have been invented. So the expensive hardware on this at this time have not been GPUs, yeah, but the Lisp machine was the interesting hardware there. And then machine learning more and more became a core topic of research in AI. At the beginning, many different approaches, let's say, for instance, random forest, neural networks, feed-forward networks at this time, support vector machines, naive Bayes, and so on. And this has been in the so-called winter without end. When you look at the most relevant conference of this time, or the most relevant conference of AI in general, ICHCAI, in this time, the proceedings are much smaller than nowadays. And you will see over the time also which topics dominated. And then came the Big Bang, with deep learning first focusing on interesting new architectures like convolutional neural networks, but then deep reinforcement learning came along. Google DeepMind won Go with AlphaGo against the world champion, which has been thought to be not solvable up to this date. And then, of course, we had the next type starting with generative AI. So I always want to discuss the difference between standard computer programs and AI programs, because nowadays sometimes people are very excited about rather simple programs and say, wow, here we have an AI program, and it is not AI. Yeah. So the crucial difference between standard computer programs and AI programs is that AI methods are applied only if problems have specific characteristics, which I point out here. For instance, if a problem is so complex that its solution or its optimal solution cannot be computed efficiently. Think about chess playing, think about something seemingly simple like a traveling salesman problem, yes? There we need heuristic methods and approximations. When a problem involves complex knowledge, which you cannot easily represent in standard data structures, which are basically lists or trees or graphs, and when you need domain or even common sense reasoning, knowledge-based methods are what you use. And the last point is nowadays the most interesting one. There are many, many problems where when we talk about humans, we speak of implicit knowledge. One area of implicit knowledge is perceptual knowledge, like recognizing a cat or a chair. And there, the knowledge-based approaches cannot be applied because we are not even able to describe the problem to the full. And in this case, we use machine learning, where we replace explicit algorithms by black box models, which are generalized from data. So while standard programs in general can always be fully inspected, maybe even verified, at least systematically tested, and we can guarantee requirements of correctness, meaning for every input in the program, we can show that the expected output is really be computed, and completeness, that this holds for all inputs. These two characteristics are typically not given for AI. Nevertheless, AI is useful, even if it's never fully correct. Yeah. Interestingly, maybe when we talk here about consciousness and relations to human intelligence, typically AI systems make rather different errors from humans. For instance, a machine learning model might confuse an ice beer with a refrigerator, yeah, which a human would never do. So that errors are often very different. There are several labels around when you talk about AI. Most AI systems are restricted to one specific domain. There we speak of narrow AI and not of general AI. For instance, when you train a model to classify animals, this same model can definitely not classify traffic signs or skin cancer. But often, and this is maybe due to the labels we use, like reasoning, learning, perception, decision-making, and so on, people have the tendency to anthropomorphize AI systems and assign characteristics which are simply not there. In general, in everyday life, we use the term intelligence rather different from the use in AI. So typically we associate intelligence with high intelligence, and we are impressed if somebody is doing a PhD in physics or plays chess on a rather high level, but we are not very impressed if somebody can recognize a cat or load a dishwater. But these have been for the long time the really, really hard problems. So object recognition basically is now solved, if you want to say, with CNN architectures. But loading a dishwasher is still an open problem. Think about the complexity of that, what you need to do on the level of planning, but also on the level of psychomotor coordination. on the level of common sense knowledge, like what is breakable and not, and so on. It's really very complex. Most AI researchers, including me, are concerned with algorithms which can solve specific problems and are not making claims about or are concerned with the question whether AI systems can have intelligence similar to human intelligence. So typically, you speak of AI. AI simulates and is not equivalent to human cognitive processes. Here we speak of weak and not of strong AI. Then there is also a group of researchers in the domain of so-called artificial general intelligence, which strive to approaches which are similar to human intelligence in a general way. So this is kind of my credo, which I take from Johnson Laird, from a book, a very well-known cognitive scientist, The Computer and the Mind. And I think it's very fair what he says here. He asks, is the mind a computational phenomenon? No one knows. I think that's a fair answer. It may be, or it may depend on operations that cannot be captured by any sort of computer. Theories of the mind, however, should not be confused with the mind itself any more than theories about the weather should be confused with rain and sunshine. So when you calculate a weather forecast in your computer, it doesn't rain in your computer, obviously. And what is clear is that computability provides an appropriate conceptual apparatus for theories of the mind. This is another point. Typically in cognitive science and very often in AI, we look on a level which is not really there. We don't look on the brain, on neuroscience, but we look on a higher level, which is the mind. Okay, I think that's enough from this. When you look at computational approaches to human information processing, which started with the cognitive revolution back in the 1950s and end of the 1950s, you can observe several things. First, we already heard this is in a talk on Tuesday. There is the Turing thesis. Everything is computable. Everything computable is computable by a Turing machine, meaning that it can be implemented by a general programming language. This was in the talk of Leonard Bloom, for instance, focused. Consequently, we need to ask ourselves, can human information processing be modeled by a Turing machine? The problem is that one and the same input-output behavior in general can be realized by infinitely many different programs. Yeah, so we also heard about this on Tuesday. We have only functional equivalence, but not structural equivalence. When we just show that some specific intelligent behavior can be simulated, this is only a proof of concept. Yeah, we only know that in principle this can be computed, but to relate it to the way in which this function is realized in the human mind, we need further constraints. So definitely Turing test is not sufficient. A first proposal to get more precise has been the physical symbol systems hypothesis of Newell and Simon, who defined a physical symbol system or a formal system such that it takes physical patterns, symbols, combining them into structures, expressions, manipulating them using processes to produce new expressions. That's basically a Turing machine again. So the hypothesis from them was very strong. Newell and Simon, pioneers of AI research, proposed that a physical symbol system has the necessary and sufficient means of general intelligent action. And this brought lots of philosophers on the plan discussing this and contradicting this, because this is a very strong claim and strong AI. Basically, this hypothesis, as it has been formulated originally, says human thinking is only symbol manipulation, necessary condition. On the other hand, it also says machines can be intelligent, sufficient condition for intelligence. Lots of problems have been discussed in this context, like Harnard with the physical grounding problem. How do we really relate these internal symbols and expressions with the external world? It has been pointed out that this is syntactic and not semantic information processing. Jerry Fodor, a well-known philosopher, proposed mentalese as a means maybe out of that. Some people said neural networks, yeah, they are different, yeah. But basically, even multiplication of real valued numbers, which is what neural networks are, basically, and nothing else, on a computer is also simple manipulation. You don't have real numbers on a computer, obviously. And in generally, it had also been observed that in neural networks, you have no relation at all between semantics and computation. Example, when you train a classifier to discriminate between cats and dogs, and you afterwards feed this same classifier a completely different image from a refrigerator, yeah? The system would either output cat or dog, maybe with a low confidence, but it would give an output, cat or dog. A human would say, oh, wow, this is something I don't know, tell me. Metacognition, out of distribution recognition. So some years ago, I had the pleasure to collaborate with colleagues from Valencia about the question whether computer models can solve intelligence test problems. And we have a paper on this in artificial intelligence and a follow-up discussion, can machine intelligence be measured in the same way than human intelligence? And basically to the core of this paper is what you see here on this graph. When we want to test whether some entity is intelligent, we have very different approaches to do this. So psychometrics does systematic testing, yeah? Algorithmic information theory looks at the problem complexity. Cognitive models like ACT-R or Clarion or Dörner's Psi model, Dörner here from University of Bamberg, take constructive approaches. We can look at performance on specific tasks, which is what classical AI does, or we can observe or interview, which is the Turing test way to this question. When we give a closer look at what makes a problem difficult, we can look on item difficulty and see that psychometrics, cognitive modeling, and AI all contribute to this question. So in psychology, you typically only look at population performance, but you don't look, why is this item in a Raven matrix test, for example, more hard than another one? You get these insights in a better way from cognitive modeling. So is an AI program which can successfully solve a broad range of intelligence problems intelligent in the way humans are? An obvious counterexample is big switch approaches. You could just implement algorithms optimized for each of these specific tasks and then make a big switch, or maybe an ensemble learner when you want to be more fancy, to decide which of these approaches to use to solve which tasks. This is obviously not what we mean. Maybe there are approaches which can solve a large variety of tests by general principles are nearer to the point. And this is the claim of research called psychometric AI. So in this named paper, we made an extensive list of many systems which have been proposed in the area of AI about these solving different types of intelligence tasks like letter series, number series, geometric analogies, Riemann progressive matrices, and so on and so on. Most of them can only solve one of these intelligence test type tasks. There appear systems from my group in this list, And one of our approaches, Igor, really addresses this question: can we use one and the same algorithm for very different types of problems? So Igor is kind of a general rule acquisition device which learns recursive functions from very small sets of examples or observations. And it was originally designed as an inductive programming device, learning functions from input-output examples, but we could show that it can also learn Tower of Hanoi in a very short time from 3 examples. It can learn simple phrase structure grammars, and it can learn solving these type of number series problems. So one of the most interesting areas of intelligence test like tasks nowadays, I think, is the abstract reasoning challenge. And Johannes from my group, who is here, has the job to maybe make further progress in this domain, because when you check this out on Kaggle, these are so hard problems for AI programs that there is a big reward given when you come up with a computer program solving these types of problems. Yeah, so Johannes, whom I just mentioned, worked on a related domain of problems, Raven progressive matrix problems. I think you all should be able to solve the one here on the top, but believe me, there are very hard ones where you really struggle to solve it. And Johannes proposed a neurosymbolic architecture where he combines segmentation learning with high-level learning on the level of inductive logic programming. So I think, again, I talked too long, as always. I still have some minutes. Okay, great. So analogical reasoning has been addressed as a really hard problems where humans excel in many different AI approaches. And we have a huge variety of problems in this area. I just showed you visual analogies, but there are also semantic analogies, like a painter is to a brush, like a doctor to what? And for many of these semantic analogies, we humans are extremely good, and we get very robust answers over big representative samples. Yeah, not so for large language models, for instance. When you look here, a painter to a brush is doctor to. A doctor can be compared to a brush, that in the sense that both are tools used to perform a specific task. A brush is a tool used by a painter to apply paint, while a doctor is a professional who uses their knowledge and skills to diagnose. Both a brush and a doctor require skill and expertise. So this is not what we wanted to hear, right? And I tested this out for many things, but of course, also in large language models, we have progress. And there is a very nice paper out by Keith Hollyoak's group, where he investigates this type of letter string analogies and compares large language models and human performance. Gary Marcus, who always has big discussions about big questions with Benjo, makes a strong claim that AI systems, currently also not LLMs, are good at common sense reasoning. And I will give you an example. 2 children, Chloe and Alexander, went for a walk. They both saw a dog and a tree. Obviously, both children can see, right? They both saw. Alexander also saw a cat and pointed it out to Chloe. She went to pet the cat. Did Chloe see the cat? We all already inferred that obviously Chloe must have seen the cat, but an LLM cannot infer, at least not when you, without further technology around the LLM, right? The LLM per se has no ability for common sense reasoning, and here reasons in quotes says Chloe didn't see the cat, which is absurd. So up to now, I only talked about typically achievements which can be measured in intelligence tests. And this might be one aspect of the question of consciousness. Basically, I talked about conscious thought, maybe partly about unconscious thought also. But I think consciousness is more than what I talked about until now. Consciousness also should involve metacognition, intentionality, self-awareness, and qualia. And I really like this quote of Oscar Wilde, where in the end it says, "It is in the brain that the poppy is red, that the apple is odorous, and the skylark sings," right? And these are experiences I am reasonably sure an AI system will not share, but I'm also sure that some people in the room might have a different opinion here. So to conclude, AI systems can simulate many aspects of human reasoning, problem solving, and learning, but general AI requires consciousness in a broader sense, including the four named components. And one neuroscientist researching consciousness, Christoph Koch, nowadays, and there he changed his opinion, come to the conclusion that consciousness in this broad sense cannot be computed in the standard sense of Turing computation. Thanks a lot.